So, our next speaker is Ulrich Landebar, and it will talk about programming reconfigurable device. Let's applaud him.
Yeah, thank you. So I'm going to have a short talk about using reprogrammable devices or reconfigurable devices, namely FPGAs, within Linux-based systems. We use the recently mainline ported FPGA framework that has been written by Alan Tull, that is working for Intel. And I think last year on the FOSDEM there was already a speech about that, a talk that was a longer one, but sadly that is lost, so the video is not present anymore. So why we came across this topic is we implemented a system that accelerates cryptography engines by that's the traditional one, the software driver running on a CPU, and we moved that into an FPGA here. And that's basically what we did. We needed some more subsystems. That's the hardware driver that talks to the AES hardware engine via DMA. And that actually integrates that into the crypto API within the Linux kernel. That leverages the accelerator, the hardware functionality, and exposes it to all system portions that want to use it. So that could be user space tools, the same as kernel space tools, because all of them can talk to the crypto API. And this way, we have a very flexible interface to our new hardware. Then, as cryptography algorithms advance and the systems change, you also want to be able to change the baseline cryptography algorithm. That's why we use a reconfigurable system, so we can swap out the old algorithm and swap in a new algorithm, or move more of them, whatever. And for doing that, we use the Linux kernel FPGA framework, and that's shown here. We have the internals of this framework shown here in the slightly darker blue than the other one. And that handles all the FPGA-specific parts. And the user actually influences what happens via device tree overlays. I come back to that in the next slide. And you obviously need some drivers that interact with the physical device. And that's those ones here that are specific to whatever FPGA device you use. In our case, this was a multiple system on chip type of platform. So we have those CPUs, actually it was two, and the FPGA part on one single chip. But other configurations are just working the same way. So you have the FPGA region that represents a physical region within the reconfigurable device. Then this one is configured by the user here, as mentioned, via the device tree overlays. The FPGA manager over here manages the association of which firmware, or in this case, bitstream actually, is loaded. And that's also leveraging the standard Linux interface structure for firmware loadings. That's the same device, system that's also used by USB systems, for example. Then the FPGA bridge part decouples every device-specific things and uses the decouplers and the configuration access port. This port actually loads the firmware into the FPGA configuration memory, and the decoupler is associated with those little devices. And during the reconfiguration process, that decouples what is in the region from what is in the outside of the region, because the behavior of logic within the region isn't specified during the reconfiguration process. Yeah, okay. So how do we actually trigger a reconfiguration, and how to separate what we want to specify, what goes in there, like parameters, platform drivers, or the bit stream itself. That's done via the device tree overlay. So every region that is within the FPGA has a stub representation in the overall system device tree. And by loading this overlay onto these addresses, the actual process of reconfiguration is triggered. So we put the device tree overlay loaded into the currently present device tree. That triggers the reconfiguration process, which is shown in the next slide. And the AES bitstream is configured into the FPGA, and afterwards the driver is loaded and the system is fully operational and can use the new hardware. So that's the process of reconfiguration. We have the configuration part and the deactivation, I would say. And it's a multiple of steps. The coloring, I come back to that later on. So we start with loading the device tree overlay as already presented, and this triggers the bitstream loading part interacting with the firmware subsystem. And when the firmware is available, the devices are decoupled so to make the FPGA ready for reconfiguration and do not disturbing any other parts in the FPGA that keep on working. And then the actually done reconfiguration is executed. That uses the program and configuration access port and loads the bitstream into the FPGA, which is actually one of the steps that contributes a larger amount of time to the overall process. Afterwards, if this configuration is completed, the region is coupled again, so that from this point on, the hardware can be accessed that has just been loaded into the FPGA. And after that, the change that has just been done to the hardware needs to be reflected into the device tree so that all other systems now know and are aware about this new hardware. So this is the application of the device tree overlay. After that, all the other subsystems that might be involved and might use this new hardware now get triggered. So the driver is loaded that is specific to this new hardware, and all the subsystems are initialized, like in our case, the support for the crypto API. Then the system is ready, it can be used. That's this cycle, that's usually people are interested in. But as you have reconfigurable systems, you also want to know how fast can I reconfigure a system, how long is my, let's say, dead time in case I cannot actually use the resources I have within the system because they are bound within this process here. And that's why we started to have a closer look at it, which steps are executed and which take how long. And that's coming later on then. So let's say the execution phase ends at some time. You have encrypted your file or whatever you have been done. And then you go on. You want to reuse this region. You want to put another algorithm into the device. The platform driver is unloaded. The DTO, the device tree overlay, is removed from the currently present device tree. And the region is decoupled again from the system. So after this step, we are ready again, and the complete process can start all over again. Let's come to some of the results that we obtained during measuring the system. So as there are a couple of steps involved with drivers from the chip vendor and also some more subsystems within the kernel, we used ftrace to gather information about when functions were entered and exit during the overall process. Then originally the intention was to show or to see what the performance of our accelerator was, but then we discovered about this interesting process, and now we present this results because they are more general, interesting than our specific ones. And yeah, we used ftrace for this. Our bitstream size, so the size of our accelerator was almost 6 megabyte that have been loaded into the FPGA. And this overall process, so all of that took about 135 milliseconds. And so you see, if you want to change the encryption algorithm for your hardware accelerator to, I don't know, encrypt one email and then another one for another email, you see that probably doesn't lead to a very efficient system because you spend more time reconfiguring it than actually computing. An interesting part was to see that the second largest contributor to the overall time is actually loading the bit stream, and that doesn't involve the FPGA anyway. So it's just fetching the bit stream. That can be accelerated, but let's come back to that later. So that was what we originally also thought about was the main contributor. That's the actual configuration process itself. That's the time needed to transport the bit stream from the RAM to the configuration memory on the FPGA through various connectivity interfaces on the chip. And the third largest contributor is the driver itself. So that's also interesting, as this is not a part of the framework. So anybody who implements drivers for reconfigurable systems should think about the setup times for them. The good news is only 1% of the overall time is spent within the FPGA framework on everything else that we haven't covered in this slide. So the framework itself seems to be quite well implemented with less overhead and shows good performance. And that also leads to the next slide, as we see performance bottlenecks, especially with respect to the FPGA reconfiguration interface. That's nothing we can change about, as the FPGA vendors have to support that. Also, some issues within the fabric are root causes for that, so that communication with the reconfiguration access port is actually a bit slower than it should be. The firmware caching itself has not yet been used in the system, so that can be implemented within the FPGA framework in the kernel. That currently does not leverage the caching mechanism, which is already built in to the firmware subsystem. Yeah, additional components that have traditionally built into reconfigurable system supports are schedulers and governors, or whatever other things are needed to make an efficient use of the hardware that has just been enabled. That's hopefully intentionally left out of the scope of the FPGA manager, as that's very use case specific, and we can implement it in user space anyway. Yeah, using device tree overlays uses interfaces that are more or less stable currently. There has been developed for supporting shields and modular embedded systems like the Raspberry Pis out there, and we just reuse them for reconfigurable systems, and that works quite well for now. What would be an interesting part is getting automatically generated device tree overlay from the vendor tools, as they usually do generate general drivers for hardware parts that have been created. Some of the mappings, like addresses or offsets and such things, are known to those tools, so that could actually help with using those approach. And to get to our last slide, it is a good reconfigurable system, and we can use it. It's efficiently supports using reconfigurable systems, and the reconfiguration times are quite slow, fast, but the overhead is low, and we can efficiently develop heterogeneous systems by them because of we don't need reboots if you change our hardware. This is a traditional problem. So you get fast test cycles, you have a compatibility layer for static and reconfigurable systems, so that's not especially needed to reconfigure, but it can also be used to static systems.
Let's conclude.
That's it. Thank you.